Recording in progress.
Okay. Test. Yeah, all right, I can see the microphone moving. All right, so let's get started. So today the plan is I'm going to switch over to I'm going to share the screen and switch over to Scholar. All right, they gave me some information for those of you that were having that issue with the browser that is locked. Apparently they can't, they didn't want to reset your profiles, but they gave me a command that you can try. And apparently that would unlock it. So just give me a second. Let's open up a terminal here. All right, so the command I was given is so if you you open a terminal and you run, apparently this will work. So unlock dash Firefox. And that's it. Apparently, I was told just type that in, hit enter. Could be unlock space dash Firefox. That's what I would expect, but this is what I have in the email. I really don't know, if it works. This is just what I was given. Does it work for anyone? Guys, does it unlock your Firefox for those of you that had a locked Firefox? Huh? Is what? You're checking. How about who had the locked Firefox? You, right? Did it unlock it for you? It's doing something. Okay. Yeah, so as I said, I don't have any support for this semester, so basically they just said this command would work. If that doesn't work, maybe it would be something like this one. This looks more of a Linux approach. Try that. But otherwise, this is actually the one I was given. Okay. So hopefully that'll solve it for you. And then you'll have a Firefox browser once again. All right. So let's get started with the class. So now we're going to get into the very important aspects of modeling. So I anticipate that by next Monday, we will be doing a deep neural net. For the first one, we'll do a neural net and a deep neural net. So basically at that point, you will be able to do deep learning, okay? From an applied point of view, right? So we haven't, if you notice, I haven't really gotten into the theory. I usually get into some of the theory later on in the semester once you know how to do some things, okay? But for now, so today my plan, at least the first half, is to get into the modeling aspects now, okay? We're just gonna do a very simple linear regression today. We're not gonna do anything with neural nets or even classification. We'll have plenty of time in the second half of the semester to look at several more complex problems. Today, though, is a very important lecture, I would say. So if you think about it, we've done, we started out with what is a tensor, right? That was very at the beginning, well, kind of foundational things. Then what is a tensor? Remember, there's no way of just like, oh yeah, I'm going to understand this concept. You got to practice it basically. Okay, so just practice those exercises. On then after the tensors, right, we looked at some basic functions. Then that was followed by reading data in. We read data from text, we read data from images, we read data from CSV files. That's usually the three main sources of multimedia data that we're going to have, okay? And you have a little assignment there that should be pretty straightforward. We will have more assignments of that type as well, okay? But really right now, I'm just trying to get as quickly as possible to where we will be next Monday, okay, which is having a deep neural net. From there on, you can solve problems, right? So you can solve a lot of problems, and then the difficulties for you will be getting the data in the right format, building the architectures, okay? And of course, the deep learning course that I teach in other semesters deals with the more advanced algorithms of deep learning. But here we go as far basically as just a multi-layer perceptron. So then today, what we're going to do is we're going to build a very simple model. So I'll show you the basic pipeline for that. It's going to be very simple data. So let's go ahead. So this should be recording, and I'm sharing this terminal. So let's go ahead and get started. And so today, my plan actually, if I complete this script in the first half, during the second half, we'll probably get into some slides just to kind of lay out some of the things that we've already done in code, just kind of in our PowerPoints. So let's go ahead and move to the folder. All right. So we looked at basics with Torch. We looked at Torch and NumPy also. That is actually very important, right? So the interaction between both libraries, and we looked at reading data. So at this point, you basically just looked at things that were just very utilitarian, if you will. Now we get into the modeling aspect of this. Okay, so I would say this first script, or the script that we're going to do today, gets into the modeling of it all. All right, so we can call this, I'm going to call this one SGD. And as I said, I'm introducing the terms here. And this is a good thing because now you can start to ask questions. So what is this SGD that you're talking about, right? And this stands for stochastic gradient descent, right? And stochastic gradient descent just is an algorithm as well, and is the algorithm that allows us to learn the weights, okay? So we're going to think how we make a network, a computer, a neural net, right? And then we give it inputs, we propagate to the end until we make a prediction. We compare that prediction to the real value. And then with that, we measure the difference and we work our way back. Why do we work our way back? Because we have to adjust all the weights based on what we learned. Do you guys see that? So it's almost like in real life, like you say, I'm going to solve this problem. I'm going to fix this engine of this car that I don't know anything about, right? So you start and you tweak and you do this and that and this, right? Then go in and you turn the key, press the accelerator, something happens. You hear a sound, you compare that to the sound that you were expecting, and then you say, okay, now I need to go back and adjust what I did. So you work your way back. Does that make sense, guys? And that's kind of what we are doing here. We're going to look at how this is done in code, in particular, as I said, in PyTorch, and then we're going to get into some of the slides. Now, if you look at my GitHub, I actually have two files in there. I have one called Scratch Learning, and I have one called SGD Scratch Learning. I'm only going to do SGD Scratch Learning. However, I do recommend that if you got the book, definitely go through Scratch Learning. Scratch Learning is almost like too detailed in how it goes through that. And I thought about doing that, but I feel it's just gonna confuse you actually. So I'm not going to go through that one in class, but I do recommend that you guys do this reading, okay? Grab the script that I have on there, Scratch Learning, and then on your own, read through the book and kind of practice it. They're very similar, but there are some differences, okay? But as far as me, of the folder called Basics that I have on GitHub, this is the last script that we will do. Okay, so after we complete this one, we're actually gonna move on to my other scripts in there, which deal with deep learning. So I have the multi-layer perceptrons, and we'll start getting into that, but that will probably be next week. And then once we start those, we will start looking at real data sets, right? So we will start looking at a data set called CFAR or SciFAR 10, which is a pretty interesting data set, more realistic, 70,000 samples or so. So we'll get into that. But, but for now, we still need to make, we want to take a look at something a little bit more basic. So we're just going to look at linear regression. All right, so we're going to go to the script basics. We're going to call it, as I said, SGD Scratch Learning. So scratchlearning.py. Okay, and so we'll start here. So we'll do the full script. And as I said, honestly, this is probably one of the most important ones because it will lay out pretty much everything that we will be doing going forward. The basic structure, I like to call it a template of how we always can write a deep learning algorithm, right? Because certain things will always remain the same, other things will be modified. All right, so let's give this a name. So let's just say basics of learning. The basics of learning with a linear function. All right, so we're going to import some libraries. So import Torch, import NumPy, SNP, import image IO. Some of these, we don't need. Image IO, import OS. Now here's one that I'm not sure. I think it's already installed, but we may need to install it. It's matplotlib. Right, so from matplotlib, import pyplot, and then asplt. This library is actually very useful for visualizing things. It's a graph, it allows us to create figures and graphs and things like that so that we can visualize the data. Now, keep in mind, usually you can visualize your data when you're doing things like this, like you're starting out with very simple data sets. Once we look at much more complex data sets, you really can't visualize the data anymore because it's multiple dimensions, right? So it's, very high dimensional spaces, so it's no longer a possibility. All right, and also we're going to now introduce something else that we need, which is the optimization module. So I'm going to do import torch dot optim as optim. So this is actually this SGD in the name, right? The stochastic gradient descent, this algorithm is going to be a part of the optimization module. So we're going to need this optimization module to do the learning for us. All right. So these are a lot of things that are theoretical usually, but the libraries are meant to abstract a lot of this, right? So we really just have to learn how to use it, right? And I think it's better just to learn how to use it from an overall point of view, right? And then once you start digging deeper into things, then you can get into the theory. Now, keep in mind, PyTorch was really designed for that. It's really designed for digging deep into things, making tweaks to everything. So it's very friendly for experimentation, research purposes, etc. All right, so now that we've added some of the libraries, Okay, we've added some of the libraries. Now we're going to add some of the data here. So what is a linear regression? Linear regression is a prediction, right? It's a function that takes in a value and predicts another value. What's a good example of it? Let's say housing prices, right? You want to predict the price of a house. What do? You take in some input. What's the basic input that you take for a house? Square footage, right? So you look at square footage, you plug that in. So it's, the house is this much square feet, goes into some kind of a function, and the function predicts, oh, the housing price should be this. Do you guys see that? It's just a simple equation. So that's what we're going to do, right? So we're going to basically take a look at that. Now the equation will look something like this, right? So y equals mx plus b, right? So we've talked about that, which is we're talking about linear regression. So we're talking about the function of a line. Now the m here, we usually by convention change it to w. Okay, so it's going to be, like this. So we multiply w times x and then plus b. X in this case would be what? It would be the square footage. And then this one would be the price of the house. Okay, and then we need to learn, though, these parameters. We don't actually know what w is. We don't actually know what b is. Believe it or not, machine learning is that. That's deep learning. That's machine learning. It's just a more complicated version of this. Okay, more complicated version of this. So we will start for our basic example with this, and then next week we will build up on top of this to now deal with images, for instance, much more complex problems. But what's so great about this is that the template that I'm laying out right now is the basic template that you can just use, regardless of how complicated a problem is. How advanced an algorithm, I always try to fit it into this template because I feel comfortable. I know what things are already well known, and then where I need to make some of the changes. All right, so I'm going to go ahead here, and now I need some data. Now I'm just going to use some data here, nothing big. So I'm going to say data C and data U. Okay, so we've got our two data sets. And then just keep in mind this now, we can change this equation to reflect this data. So we're going to say we have some real data that we predict TU given or actually, sorry, we're going to predict TC given, maybe what I'm going to do is y equal wx plus b. And now we're going to write it in terms of the data that we have as t underscore c equal, and then it's going to be w. Let me also change this to include asterisk w. Now the x now is going to be tu plus and then b. So that means the parameters that we need to learn are still going to be w and b, but now it's going to be in terms of tu and tc. So we're going to have some actual real data here for us to learn. Very little data, but this is just to illustrate the example. Does this make sense, guys? All right, so a very simple one, but a very foundational, actually, so that we can learn how to build all our deep learning algorithms. So, all right, so now let's proceed. So I think it's, I see the green moving. All right, now let's proceed. Now let's proceed and just add the data here. So for TC, it's going to be 0.5, comma, 14.0, 15.0, 28.0, 11.0, 21. So as you can see, for every TC, we need to have a matching TU. Okay, we're gonna do some tricks with the indices here because we need to get the data and process it correctly. Okay, so now these are the TC. So the values that I'm trying to predict, they're not necessarily housing prices, right? They're just a data set. And then here we have the TUs, which are the X values, as you can see here. So that's going to be 35.7, 55.9, 58.2, 81.9, 56.3, 48.9, 33.9, 21.8, 48.4, 60.4, 68.4. Now I'm taking my time with this, and the reason is that this is extremely important, right? So I want to stress some things here. So these are pairs, right? So basically the index of these needs to match. So for instance, you know, this value, they you know, I'm going to try to align the commas here, right? So if you see these values go like this, right? So the values are aligned. And what's important about this is that they have indices, right? So this is going to be index what? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. There are 10 values. Each one of those is an index, and they are aligned. That is to say, if I look at a value of 21.8, the function that I'm trying to build should predict something close to -4. If I plug in a value of 56.3, the value that the function should predict should be around 11. Do you guys see that? This is the training data that we are trying to learn from. Okay, so you know, if we plug in 68.4, it should try to learn 21, right? So that's an important concept there. All right, and so this will be crucial because this is why we learn about tensors, right? You know, and NumPy and everything, so that we can process our data. So once we've done this, these, remember, are Python lists. So we need to then convert these into tensors, right? So I'm going to say now TC equal torch dot tensor. Right, and I'm going to plug in here T underscore C. T underscore C. Right, and also we're going to repeat this for TU. I'm going to do T underscore U equal torch dot tensor. Right, and this is going to be TU. Okay, so I have the two lists of two Python lists. I've converted them now to tensors. All right, the next step I'm going to take is I need to split the data. So this is where NumPy and knowing tensor operations becomes really handy because we can do a lot of things very efficiently, right? So I need to split this data, TC and TU, into a train set and a test set. Okay, so that needs to be done because I'm going to, you know, train the model, but then also try to evaluate the model. Okay, so I'm going to do here, I'm going to split the data. So splitting the data set. Okay, and so you know, there's many ways that you could do this. This is actually something that you guys, you know, could figure out on your own, but this is just an example, an approach on how to do this. So I'm going to take, first of all, I want to know the number of samples. So I'm going to do tu dot shape 0, right? So, oops, that's enough. 0. So that's going to be n samples. All right, so let's go ahead and print that one. N samples. So let's go ahead and run this code. And of course, bash. Conda environment list. All right, and then I'm going to go into the environment for PyTorch. So I'm going to do conda activate PyTorch py36. All right, so activate the environment. And now we're going to run that script just so that we can see the number of samples. No. Oh, yeah, sorry. This will be let's let it run for a sec. All right, so it's not finding matplotlib. So that's probably conda install matplotlib. So let me just double check. It is, right? Yeah. So right. So I'm going to go ahead. Matplotlib. Yes. All right. So hopefully it'll work now. I'm going to run the code. All right, and there's 11 samples in there. All right, so now that we know that there are 11 samples, we are going to select the number of validation samples. So we go back to the script. And so we go back and we need a number of validations. So let's call it N validation. This can also be testing as far as the name is concerned. So usually it's going to be 20% of the data. So usually you take like a 80% split or a 70-30% split. So I'm going to do 20 here. So I'm going to say nval equals int. And then in here, it's going to be n samples times 0.2. Oops. So that should give us about 2 or 3. Now, this is where it gets a little bit useful to use Torch, because we want to so we are going to generate a list of indices. So basically what that means is we're going to take the list of values from 0 to 11, right? And we're going to shuffle them so that we can get a list of shuffle indices. So you'll see what I mean by this. So let's create a name here. Let's call it shuffled indices, right? And this is a common approach, actually, to randomizing your data. So the point is that you don't want to feed, you're going to have the data set from 0 to 11. You don't want to just take the first 7 always and feed them into the model and then take the last 3 and use them for validation. What do you want to do? Instead, you want to shuffle them, right? You want to randomize them in some way so that every iteration you're actually giving it, this chunk, that chunk, whatever, right? So this is a trick for doing this. So you can imagine how you could repeat this quite a bit with when you're training your model. So let's do torch.rand perm. Okay, and in here we just need to supply the number of samples that we have. So n samples. Okay, so now we want to print this out. So let's go ahead and try to print it, see what we get. Shuffled indices. So Control X, Y. All right. So what do you guys see here? You see that we created a list, right, of all the values. They're all unique, because indices will always be unique numbers, right? You're not going to have repeated indices in there. You can see here 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so now that we have these, we've shuffled the data. We've randomized the data. Do you guys see this? And yeah, go ahead. Rand perm, yeah. Rand permute, probably. Random permutation, yeah, go ahead. You can try, as I said, this is just one way of doing it. You can try any one, but this is a random permutation, so it just basically takes whatever list, whether it's 11 or a million, right? It doesn't care. Remember, it's a torch function, which means it's going to be pretty efficient. And then you just have to tell it the range, because that's really all it is. It's going to give you all the indices randomized. And then this is going to be useful because now you can slice out what you want for training and what you want for testing. Does this make sense? All right. Any other questions? Say that again. I haven't used it yet. We're going to use it, but I just haven't used it yet. So the point is, how can I say this? Let's say that you have 70,000 images, right? And you have an index for every single one. So you just do this for 70,000. Now you're going to have a list of 70,000, but it's going to randomly permute the values. So it's going to give you like this. So now what do? Just select. So you'll see me. Now what I'm going to do is I'm going to slice out from 0 to 80% all the indices. And then from 80% to the end, all the other indices. And that way I know which ones I'm going to use for validation, which ones I'm going to use for training. Do you understand? This is actually really important. And it's something that you have to do because you want to randomize your data quite a bit. And this, again, this is why when I did this, I aligned the commas and I provided these indices above, you see? Because this is now, what I mean by this is I'm going to extract some of these for training, some of these for testing. Okay, so let's say we'll print them out to get a better feel for it. But let's see. So I have the shuffle indices now. I have the shuffled indices. Now I need to extract, I need to create basically two lists, if you will, of indices. All right, so I'm going to call one train indices. And the other one is going to be val indices. Okay, so I have two of these. So all I have to do is, because I have all of my indices in shuffled indices, right? So I need to grab now these. So shuffle indices, and down here as well, shuffled indices. But now notice what I'm going to do. I'm going to do slicing basically. So I'm going to say, oops, up here. For the training, how many samples do I want in training? Well, my split was 20%, right? So that means 80% of the indices. So I'm just going to grab from 0 to 80, right? So I'm going to say for all, so from beginning all the way to negative and val. You guys see this? Remember that when you put a negative index, you start counting from that end, right? From the end of the list. So I know that there are, let's say out of 10, 3 are validation. You guys see that? So I'm just starting at the end of the list, 1, 2, 3. And I grab those last 3 for validation. Well, it should have, yeah, so my mistake is actually up here. It should be nval. Got it? All right, and then over here then, so using that same logic, what would this be? How do I remember? You gotta be able to do these slicing things, right? So how would you slice out the validation indices? Look at what I did for train indices, right? So from 0, so now how do I get the validation ones? Nval to the end, right? Yeah, exactly. So negative n underscore val colon. Do you see that? These little tricks, you know, are lifesavers. I mean, you know, in the past, you know, many years ago, I remember trying to do these things with for loops. This was not fun. Okay, so so nowadays there's great value in NumPy, tensor operations, and this is an example of it. In just a few lines of code, you get a lot done. Also, that is extremely efficient and fast. Here, it doesn't matter because there's only 11. Imagine if you had 2 million records. You know, you got to do these operations efficiently. All right, so now we have our indices. Remember, all we have is the indices. We don't even have the data yet. The data still lives in these, right? In TC and TU. We need to extract from there the pairs that we're going to use to train our model. So now what do? We need to take, oh yeah, so let's print them actually. So I'm gonna print, just so that we get a feel for it, I'm gonna print train indices. Now I'm going to print val indices. All right, so let's go ahead and run that. Right, and you can see here, these are the, out of the total indices now, right? 2, 4, 0, 3, 8, 9, 5, 1, 6. Basically these, we're gonna need to slice out those indices from the data for training purposes. And then 10 and 7, we're gonna slice out from the data for testing purposes. And this is a very common approach that you're gonna basically be doing all the time, right? So training and testing. Because you have to get your data and validate it in some way. All right, so let's go ahead now and go back to the script. All right, so now that we have the indices, the next step is going to be to actually create our train and our val. Now remember, now we need, we have originally TC and TU, right, guys? We have TC and TU. But now we're going to need to have a train TC and a val TC. And then we're going to need a train TU and a val TU. So our two data sets become 4, right? Because we need to have that for our operation. Questions, guys? All right, so then here, what I'm going to do is I'm going to do the train first. I'm going to do train T underscore U. And I'm going to do train underscore T underscore C. All right. And then down here, I'm going to do the same for val. So it's going to be val T underscore U and val underscore T underscore C. TUC, TUTC, and yeah. All right, so all we need to do now is from the original data, so from T underscore U and from T underscore C, we're going to slice out our data using these indices that we have. And we're going to do the same for val from T underscore U, T underscore C, right? We're going to slice out the data. All right, so which indices go here? Basically, train indices. So the ones we have here, train indices. And the same for this one. And then down here, now we need the indices for val. So these are, the last two that we had. So in this case, it's going to be val indices and val indices, like that. So now we have our two data sets, and we are ready now to do the operation. Usually here, you're going to normalize the data. You saw me normalize the data the last time we met. This time around, I'm going to do just a very simple thing of just multiplying things by 0.01. The reason for that is that our data here is actually pretty constant and pretty homogeneous, if you will. It's not really like all over the place. Do you see this? So really, it's very easy just to do like a 0.01 here. But we could use the more complex calculation. So down here, I'm just going to multiply. I'm going to say train TU norm and val TU norm. Right. If now TC is the predicted value, if you notice in the equation, we predict TC. We usually do not normalize the labels, right? We usually do not normalize the data that we're predicting. We only normalize the data that the X's that feed into the architecture because they have a bearing on the weight calculation, okay? A direct bearing. So if you notice over here, I'm just doing TUs, which are the X's, basically the inputs. So let's call this train TU norm, val TU norm. Oops. And oops, and then we can just multiply this by 0.1. So train T U. And then here, val T U. Okay, so really remember, I'm even going to put this in a separate space. Normalization, you should always normalize your data. Always normalize your data. Okay, so now I have my data sets ready to go, train, for training and testing. Now let's go ahead and let's try to plot this information. So this, as it turns out, this is actually temperature. This is temperature data of Fahrenheit versus Celsius. So let's take a look at it. Now, as I said, we can't always look at this data, but for our data, we can't always visualize our data. But in this case, at least for learning purposes, this should be helpful. So let's do our temperature data. So here I'm going to use matplotlib. So I'm just going to do a figure plot figure. Okay. I'm going to put in some labels. So plot dot x label temperature Fahrenheit. Plot y label temperature Celsius. Right, and then after we have the labels, let's do plt.plot. And notice here we plug in the data. So it's going to be T, the original data, TU dot numpy, comma, TC dot numpy with symbol O. All right. So now we proceed to just show it. So I'm going to do plt dot show. All right, so let's try this out, see if it works. And there it is. So there's the figure. And as you can see, it is actually, that's our data, right? So we have the TC data over there for the x-axis, right? And the TY data for the Celsius, right? And you can see it basically does have, what is this called? A linear trend. So it has a linear trend, which basically means that we could, in theory, calculate a line, right? Given these points, so that we could make predictions. So for instance, here at this gap, right? So if I plugged in like 75, I would want to predict the value around 24. Do you see that? That's the goal of what I'm trying to do. All right, this is, linear regression is whenever we're trying to predict a real valued number, such as this one in this case. If I had like 41 probably, then it should be 5, basically, is what you would want to predict. All right, so that's really the idea. And basically, as you will see as we move forward, classification, which is kind of the heart of what we do in machine learning, is going to be just a modification of this. It's a slight modification of this, but we are still calculating a line. It's just that it will no longer be a line that runs through the data, and instead is a line that tries to separate the data. So it kind, yeah, go ahead. Oh, I'll go back to it. Yeah. So, but yeah, so I'm just explaining that this is kind of the first time we visualize the data, and in our context right now, basically just to fit a linear regression here. Later on, we'll use the exact same approach, but we're going to move the line. So instead of being a line like this one, right now we're doing a line like this. In the future, we'll do a line like that. Okay. If you notice, all that it changes is like the rotation of it. Because we're going to have data that's, say, blue, red, because this is pictures of dogs, this is pictures of cats. So we want to find the line that best separates them. That will be in the future, but the intuition of it is that's going to be a line, just like this one, except this one looks like this, that one will look like that. That's the trick. I mean, it's like a fun little, insight, right? And so we'll take a look at that. So as I said, I can't write on this, but unfortunately, but here's this line like this. Classification would just be a line rotated by 90 degrees. All right, so we've looked at this now. So now let's proceed. We have a sense of the data. So I think somebody had a question about the code. So we're going to go back to the code. And you can see it here. That is a no. It's just a symbol that you're going to use to visualize. Yeah, right. Any other questions, guys? Making sense? Making sense so far? All right, so we've got our data. Now we're ready actually for the main template of modeling. All right, the main template of modeling will use functions, right? So we're going to use functions to make our code more like what to do every time, because even if you don't remember, you can always say, okay, the template is this, and then I have to fill in these different things. So let's start by laying that out. Let's lay out the template. We're done with our data. Our data is done. Usually 80% of your work will be just getting the data, getting to this point, okay? Having those 4 data sets, train and test, ready to go. I'm going to comment this out by adding these single quotes here. So now let me add actually the print on. Okay, so now what comes next is defining the actual modeling part. Usually, I like to have some functions for it. So let's do that. So first, I usually have def model, okay, and you usually actually use that name as a convention model. This is where you define the equation that does the prediction. So in our case, what does our equation for the prediction look like? What does it look like? Y equal mx plus b, right? But that's not always going to be the equation. It'll be slightly different. And we're usually going to refer to this as the architecture, because we're going to start getting into deep neural nets, which is a function of 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 a function. So it's an architecture. Okay. But for now, we always set this as the model. All right. So I'm just adding this as a comment. I'm going to take this out later. But this is the template, the placeholders, right? Then after the model, what else do we need to define? We usually need to define the way that the parameters are learned. And that's usually going to be referred to as the loss function. You will always have a loss function. Okay. So we'll talk about it a little bit. This is where we actually have to get into the theory. All right. So at this point, this will not be so simple, but this is just keep in mind where we, learn, how we learn the weights basically. So you know, we'll have to think about, so how do you train a linear regression? You know, what's the scheme, right, to train a linear regression? So that's going to be in the loss function. And that, you know, we're going to use other more advanced loss functions like something called cross entropy, etc. later on. But the great thing about it is actually Torch and TensorFlow and all these packages already provide the functions well defined for you. So you really just have to use it, okay? But it helps to actually learn it a little bit, at least for linear regression. Right, so we've got the loss function. Then after that, so we would do model loss. And then then after that, we can have other functions, but we won't have one for this. The next one is we're going to need to have what is called a training loop. The training loop. And this is going to be actually sometimes the most busy function. This is where we're going to bring everything together. It's like the main. You know, if you think about like in a regular program, you have a whole bunch of functions and you have one main. And the main has the for loop and it's got, you know, everything that you're doing together. So that's what training loop will be. Then here, I usually, this part is another, you know, I sometimes, so let me think about this. This is usually call the functions, let's call it. Call everything for now. Right, so it doesn't really have like a formal name, but it's usually where you end up calling all the functions. Okay, so you know that's that main area. Because really the training loop is one of the central things that you call here. So let's think about that. Let's think about how this works. Okay. So we're going to need to define, before we define these functions, let's think about what we're going to need. We're going to need, if we're talking about the equation y equal wx plus b, right? So we're talking about this function. We need to learn the parameters w and b, right? That's really the goal. Now we're not gonna, we could use directly those parameters. We could define a variable called w, could define a variable b, but there's a more convenient way. That's what I will say. There's a more convenient way of doing this. And that is to create, at least in PyTorch, to create an array, if you will, a tensor that is going to have all the parameters in the one tensor, okay? So like the W and the B are now going to be in just this one tensor, okay? And that's very useful because you sometimes want to look at that data, you want to move it around, you know, and so you can just move one whole thing, you know, one parameter, it's together, all right? So we're going to create that. So here it doesn't seem like much because there's only two parameters, but believe me, when you have hundreds or, you know, many, you know, it does make a difference. So here you can see I'm doing torch.tensor. Okay. And so torch.tensor, and then we specify, we initialize basically the parameters to 1.0 and comma 0.0. All right. So we initialize, that's your W and your B. Okay, guys. So that's your W and your B right now. We're just seeing how to define this in a very simple way. Later on, you know, it might be tensors themselves, right? So where the 1 and the 0 is located, we would have to define dimensions and things like that. But for now, let's just do it like this. And here, though, there's one little, the way that I would say is this quirky thing about PyTorch. PyTorch has these things that are kind of strange, but they're actually useful later, right? And so it's good to have them in there. So one of the things that you can specify here is something called requires grad. and you set it to true. What this means is that, these parameters are completely associated with the computational graph, and they're completely associated with gradient descent, the process, the algorithm that updates them. That's really all you need to understand right now, is that W and B need to be updated, okay? And so usually this flag is used to control updating. You know what I mean? So it's like, we're in the training process. We definitely want to update the parameters. So requires grad means gradient. So requires gradient. So true. So it means update them. Do you guys see that? But there might be other situations where, like we're validating the data, we're just checking that the model works, but we do give it more data, right? So we want to tell to the model, do not learn from this test data, for instance, because you really should only be learning from the trained data, right? But we still need to test to see how it's performing. So in those particular circumstances, what will you say? You'll say requires grad equal false. Do you guys see that? So it's a control that PyTorch has, and it's kind of something built in that it has, basically. Make sense? Yeah, go ahead. You can, yes. I'm just initializing. Yes, that's right. So you can define these however you want, and they're actually much more complex than this. Remember, when we're doing, that should be random, right? So really, that should be a uniform distribution or a normal distribution, because the initialization of the weights and the biases is actually really important. But for this example, I only have 11 samples, so it hardly matters. Do you understand? We will see a lot more of this, believe me. All right, any other questions, guys? All right, so yeah, so again, these are the things that we're going to be initializing, the weights and the biases, and then requires grad, etc. The other parameter that, again, remember, a lot of these things are new to you. What's great about this, though, is that right around next week, a lot of the new kind of decreases, right? The quantity of new things, because we just start reusing things, and things will start to become familiar to you, and then you'll understand. So, but right now I'm going to introduce another term, which is called a learning rate. All algorithms need to have this. What is the learning rate? The learning rate is a step, if you will, or it's a delta value that defines by how much do you modify the weights and the biases. Do you see that? So let's say that you have a weight, right? And it's 3. And then you decide, I'm going to update it either plus or minus. That's determined by calculus, something internal in gradient descent. But then you could say, okay, plus or minus what value, right? Should it be like 0.5, 0.7, 3, 0.001? You guys see that? So that little value controls by how much you update the weights. And that is controlled by the learning rate. Right? The learning rate just means how much do you adjust the values. So obviously it means that if you want to change the weight a lot, if you have a very tiny learning rate, well, it's going to take a very long time to change it. You see that? On the other end, if you have a very large value, it's going to be very fast, but you're going to miss some values along the way because it just jumps really fast, right? So if the adjustment is 0.5, it goes from 1 to 1.5 to 2 to 2.5 to 3, right? If it's going up. But if it's 0.001, it goes 1, 0.01, 1.002, 1, so it's much smaller or slower, and that gives you a little bit better to try out more values. So it's usually a balance, but here we can say that something like 0.001 is a good number. All right, 0.001, somewhere along that. So in this case, I'm just going to use the exponential notation here, like that, okay? Just so that you see something different. We could have written 0.001. Does this make sense? All right. So we've defined the learning rate. Now the next, we have the parameters. Now the next thing we're going to define is the optimizer. And the optimizer is the mechanism that we're going to use to train the model. This is a complex thing, okay? It's a very complex thing. We'll take a look at all of this later. But for now, I just want you to see all the mechanical pieces together. So from the optimizer is a variable. If you notice, we're going to be using from the very top when we did import torch optim as optim, right? So we're using that part of torch library, which has all the optimizers. In our case, it's going to have the stochastic gradient descent, which is the algorithm that makes all of this possible. All right, so I'm going to do optimizer optim dot SGD. You see that? And that basically means that I'm going to use the stochastic gradient descent algorithm to learn the weights. Okay, so I just need to kind of define this. This is what I want to use. Okay, so what do I plug in here? I need to plug in here the parameters. And I need to provide in here also the learning rate. Remember, because it's programming, you define a whole bunch of functions, and then all of these functions have to somehow be linked together, okay? And in the end, you end up forming what is called a computational graph, which is basically, it's a graph that of nodes and links, right? That connects data to functions. Okay, so there's functions that operate, there's data in tensors. The tensors flow through all these functions and until you get your final result. Okay, but so right now we're defining all the pieces, all the functions that will allow us to build this computational graph. So this piece, the optimizer, optim.sgd. Notice that here we conveniently plug in the parameters, the W and the B, okay? And then here we have the learning rate as well. And as I said, remember, this allows us to move these variables easily. Now there's another one called the atom optimizer. So you've probably heard of it. So if you're already aware of this, you just plug in atom. Okay, but we're not gonna use atom right now. We're just gonna use the stochastic gradient descent, but this shows you that these things are changeable, right? So you can modify them and have different kinds of things. All right, now that we've defined the optimizer, now we make a call to the training loop. Remember the training loop, we haven't defined it yet. We'll probably define this during the second half of class today. But that still needs to be defined, okay? Still needs to be defined. However, what I said is this is really important today because this is the template that we're going to be using most of the semester. All right, so now what is the training loop? The training loop usually provides a result, some kind of a result, a value. And that result can be printed out. So we can do print result, for instance, like that. See that? All right, and then here we make a call to training loop. Okay, and we need to specify a lot of parameters in here. Okay, so this is where we kind of bring everything. We pass everything as arguments into this. So obviously the training loop is usually the one of the most complex functions to set up. Also the architecture obviously can be complex to set up. Okay, so let's start with yet another parameter called epochs. So I'm going to set this to 3000. So what does that mean, epochs? What happens in machine learning is that you really take all the data, right? You take all the data in your training set and you feed it to the model. And then guess what you do? You grab all the data again and you feed it into the model. And then guess what you do? You grab all the data and you feed it into the model. And you keep doing that by a number of epochs, such as 3000. Now, this is where the randomization is very useful, right? This function really, although I only did it once here, really should be done in the loop. Every iteration, feed the data randomly. Do you see that, guys? Because neural nets have a tendency to learn the pattern, right? So you need to change the data every time, the way that you give it, so that it tends to like generalize more, just to be a little bit better with that. Okay, but that's actually what this is doing. It took me, believe it or not, and I'm slow to learn sometimes. It took me a very long time to understand this concept, this epochs concept. It was just like, it just didn't make sense to me. Why are we repeating this 3000 times? We already fed it once, right? So that should be enough. But as it turns out, neural nets actually do better when you do that. Okay, because when you're talking about millions of records, you know, it does make a difference, a huge difference. Is this clear for everyone, guys? All right. So n epochs is really that, is that repetition, okay? Is that repetition that you're gonna have in there. You'll see that it's gonna get a little bit more complex. The other thing that we're gonna add, obviously, is the optimizer. This is, by the way that this code is written is the way that something like Keras is written, for instance. The Keras in TensorFlow, if you've ever seen it, is basically behind the scenes. It's written this same way. So they're all very consistent, is what I'm trying to say, in the way that they've developed it. As you guys know, I've used TensorFlow before for many years, but you know, I really like PyTorch now. I just like the way it is, very flexible. So anyway, so here we add the optimizer that we defined up here. Okay, so we're going to do optimizer, comma. And then we have params. That's the params that we defined, so we need to pass that as well. And then we're going to pass the data. So the data is going to be train P_u, and it's going to be val tu, and it's going to be train tc, and finally val tc. Right, so this is our data samples, basically. So train tu, so the way I did this, because really we're going to pass the normalized data. Okay, so we're going to pass the normalized data in here. So if you look, we're going to pass this one, train tu norm and val tu norm. So those are the values I'm going to plug in here. So train tu norm and val tu norm. And then train tc. And val. Does this make sense? So we're just passing all of our data. So our data through this function conveniently. The names might be different, but we're passing it into the function. And hopefully it makes sense, the train set, the test set. All right, so we've basically defined the main loop here. We're ready now to define these individual functions. So we're ready to define the model, the loss function, and also the training group. Okay, so that's where we are right now. So it's actually 3:18. So let's take the 10-minute break here, because this is a good stopping point. And then we'll come back and it'll give me a chance to generate this video. And then we'll continue with the rest in the second half. Make sense? Let's take a 10-minute break and I will begin to generate the video.